Uh, unfreeze the screen for you all. Okay, so reducing down square root of 8. Again, that's something we did first semester. And when we're reducing square roots, or any roots for that matter, okay, so for everything we're doing today, we're looking to factor out the perfect squares, okay, or if we're working with cube roots or fourth roots, perfect cubes, perfect fourth roots, all those kinds of things are what we're trying to reduce or to factor out of here. We're going to keep most of our focus today on square roots. Remember, square roots are if we don't see that like actual number in this actual kind of root form. So all this is being square roots. Okay, so we're looking, when I see root 8, I'm asking myself, what numbers factor 8 that I can take the square root of and they equal a whole number? Those are the perfect squares. And when we did this first semester, for those of us that don't know the perfect squares, I always recommended that you list them out. So writing out 2 squared is 4, 3 squared is 9, 4 squared 16, so you have that whole list in front of you and you're like, oh yeah, I want to factor out a 4 and rather a root 4 because I can take the square root of that to get 2. Then the root 2, there aren't any other perfect squares that divide that, so we consider that, or at least I call that a dead end, meaning there's nothing more we can factor from it, or at least not any other perfect squares. So the simplified version of root 8 is 2 times the square root of 2. So we're always looking to factor out perfect squares. Now, what we're adding on that we have not seen yet is just taking square roots of variables. Idea is kind of the same. There are perfect squares with variables. Okay, and if we remember x squared, how we undo squaring anything is we take the square root of it. Now, knowing that these cancel and they give us just x. There's a couple other ways that I want to show us how we can get to this because it'll make more sense for some of the other ones that might be a little more confusing. So let's take another approach here. And let's say we want to simplify the square root of x squared. Well, I shared a property with you all back with our log unit that if we're taking the root of something, that has an exponent. Remember, all roots have a fractional exponent. So I could write this as x squared all to the power of 1/2. Well, if I have an exponent raised to an exponent, I can multiply those exponents. So 2 times 1/2, that's 1. So I get x to the power of, or let's actually show it, 2 times 1/2 is 2 divided by 2, and 2 divided by 2 is just 1x. Now, there's something odd that kind of happens with this, and it's all about it being mathematically correct. And this is going to be the most confusing part of all this. So technically, when I take the square root of x squared and we say that is just equal to x, that's not entirely true. And here's why. Let's pretend that we let x equal -3. And so I plug this in. We're going to plug it in and check our work. Is the square root of x squared equal to just x? Well, if I plug in -3 into the square root of x squared, I get -3 squared. And we're checking, does that equal -3? Okay, so plug -3 into square root of x squared, plug in that same -3 to what we think it equals, being -3. Well, what happens here when we square this -3, it turns to +9. Well, that's a good thing because for us to take square roots, it needs to be positive, but the square root of 9 is +3. So based on this, we're getting that 3 equals -3. That's not a true statement. And so what this is telling us is the square root of x squared is not necessarily equal to x. There's something we need to do to that x that they do end up being equal. And somebody think off the top of their head, what can I do to any number to make it positive? Take the absolute value of that number. So really what happens here, we need to say that the square root of x squared is equal to the absolute value of x. Now, how are you supposed to know when to apply the absolute value? Here's that property. If we are taking the nth root of a to the power of n that is going to equal A, so just the most basic version of it without the absolute value brackets, if A or if N is odd. So if we're taking odd roots, this absolute value idea doesn't matter at all. Okay, it's only applying if we're taking an even root. So it equals the absolute value of A, like what we just explained here, if N is even. Okay, just so that we can say that they're 100% equal. So what we need to have on our radar is if we're taking the nth root of some power or some term raised to some power and that power is even, we need to include absolute value brackets. So let's see how this applies to the square root of y to the fourth. Square root of y to the fourth. Again, one way to think about this is y to the fourth to the power of 1/2. Any exponent raised to another exponent is just those being multiplied. So that gives me y squared. So right now, we're saying the square root of y to the fourth is equal to y squared. This y squared, well, let's think about this property here. I took an even root of an even number, and so basically we're saying this should have absolute value brackets, right? That's exactly what this property is saying. Okay, if n is even, which it is in this case, we have an even root, even power. We're saying we need absolute value brackets. Are they 100% needed here, though? What do you know about y squared, and what's the result of that always going to end up being? Positive. So if you write the absolute value brackets, that's okay. It's just more redundant because y squared is already positive. I think for now, I'm just going to add the absolute value brackets in. That way we have that on our radar. And then for those of you that are seeing like, hey, y squared, that's already positive, I actually do not need the absolute value brackets. That's even better. Okay, so to kind of conclude here, here's what we'll say. Square root of y to the fourth is really just equal to y squared. We don't need the absolute value brackets. The absolute value brackets are redundant because y squared is already positive no matter what. Just to keep it consistent, though, we'll say that it's the absolute value of y squared, which will always end up being positive anyways. Okay, well, what we're going to do is we're going to take each of these individual pieces and see if we can't simplify an entire expression that has all those square roots all in one. So really what we're working on today is simplifying these type of expressions, okay, where we're taking the square root of more than one term. Well, we've essentially done this in the opener, okay, or in these first three things we've talked about here. So when we see the square root of a lot of these terms, to me, it's helpful for us to think about us taking the square root of these individually. So instead of this being the square root of 8 times x squared times y to the fourth, we can say that it's equal to the square root of 8 times the square root of x squared times the square root of y to the fourth. And we treat them all as individual simplifying problems, where we just did all these. We said that root 8 was equal to 2 times the square root of 2. We said that x squared was equal to the absolute value of x. And then we said that y to the fourth is equal to the square root, or excuse me, to the absolute value of y squared. And so our simplified expression here are all of these things just simply being multiplied together. Okay, so what we'll do is anything that's within the absolute value brackets, we'll put it all underneath absolute value brackets. If something's being square rooted, we'll put it all underneath the square root. Okay, so I'm going to say 2, that doesn't have absolute value brackets or square root. Then we'll do our absolute values of x, y squared, and then times the square root of 2. So this entire expression simplifies to be 2 times the absolute value of x times y squared times the square root of 2. And again, break them down so you're just dealing with one piece individually. Okay, I'm going to ask that you all try your very best to simplify number 2. And let's do this. Let's do these all individually. And I don't like how I space this out here. But we're going to try to work on simplifying square root of 48 times the square root of x to the 4th times the square root of y to the 8th. Okay, see what you can come up with right now. Just give a guess. There is no penalty in trying. See what you come up with. And we've got just a couple more. We're going to save the backside for tomorrow. Okay. So let's look at each of these terms individually, starting with the square root of 48. The easiest way to reduce down all the numbered square roots is to factor out the largest perfect square that divides 48. Again, I don't recommend picking any random factors of 48. I know that's maybe how some of you were taught how to reduce these down, but that can get really complex and creates these really long factoring trees. Okay, so I always look for the largest perfect square, which the largest perfect square dividing 48 is 16. So I factor root 48 to be root 16 times root 3. Square root of 16 is 4. Root 3, there aren't any other perfect squares that divide it. So root 48 simplifies to be 4 times the square root of 3. Then square root of x to the 4th. Since I'm dealing with square roots, and since n is even in both these cases, I'm thinking that I might need absolute value brackets before I even deal with the simplifying there. Square root of x to the 4th. Think of that as x to the 4th to the power of 1/2. So we're just dividing that exponent by 2, giving me x squared. I'm putting it inside absolute value brackets because of us starting with the even root. X squared is positive no matter what, so you actually do not need the absolute value brackets here. Okay, the absolute value brackets are basically redundant. Okay, they're just doing the same thing over again. They're not needed, but I am going to keep applying them just so that we're keeping them on our radar. Okay, it's not mathematically incorrect if we have them. It's just redundant. All right, very similar idea to square root of y to the 8th. Dividing that exponent by 2 makes that y to the 4th. Again, I'm using absolute value brackets because of us starting with an even root. And thus, when I combine all of this, the most simple way to write this is 4 times the absolute value of x squared y to the 4th times the square root of 3. All right. Any questions thus far? Before we work through just one more example here, or 2 more. All right. So now there's just a couple more things we're going to add on to this and talk about what do we do with like x cubed and y to the 5th when these exponents are odd. So we're going to combine all 3 of these things to eventually simplify 2 times the square root of 75 times x squared or x cubed times y to the 5th. So it's this problem. We're going to say that we're going to split this up right away, just like we've done before. So we're really thinking about how do we simplify 2 times the square root of 75, and then that times the square root of x cubed, and then that times y to the 5th. So for each one of these, we'll simplify them individually up top here. And let's start with the 2 times square root of 75. With root 75, I'm looking for the largest perfect square that divides 75. That is 25. So I'm going to factor 75 to be 25 and 3. 25 times 3 is 75. I'm still taking the square root of both of those terms. The square root of 25 is 5. Root 3 is a dead end, so there's nothing more for me to do there. I also have this 2. So 2 times root 75 is 2 times 5 times root 3, making it 10 root 3. Okay, so we multiply all the dead ends after we've simplified it, including that coefficient in front. All right, here's the issue with us trying to take the square root of x cubed. If we think about this with the fractional exponent, we can think of this as being x cubed to the power of 1/2, which is x to the 3/2 power. Does that simplify down to be a whole number? No. So there's still a square root in it. There's still, we still have that root there. So getting to this x being the square or x to the 3/2 power isn't all that helpful. So really, when we see this square root of x cubed, we have to factor it just like we do with numbers. And we have to factor it so that we can get a perfect square to show up. Well, with perfect squares, that's what we just did. Okay, we need the exponents to be even. So we're going to factor x cubed to be the square root of x squared times the square root of x. X squared times x is x cubed. Okay, so we're just factoring. Okay, we're breaking it up so that we can take the square root of x squared. That's x. That's an even root, so I should have absolute value brackets around it. And then root x, I can't factor out any other perfect squares from it. So this simplifies, or our dead ends here are root x and the square root of x. And thus this simplifies to be root x, or excuse me, absolute value of x times root x. Okay, and then y to the 5th, exact same idea. We need to factor it so we get a perfect square to show up. Well, the smallest perfect square, or excuse me, the largest perfect square is y to the 4th. So I'm going to factor it to be y to the 4th times y. Y to the 4th is y squared. Since it was an even root, I should include absolute value brackets. Not 100% necessary because y squared is already positive. Okay, but we should have those absolute value brackets. At least I want them on our radar. And then the root y has to stay as root y. There's no other perfect squares that divide it. So this is root y, or excuse me, absolute value of y squared times root y. And so now we've simplified all three of these individually. Thanks, buddy. And now we just need to piece this all together. So to piece it all together, we'll multiply anything that's not being absolute valued or square rooted individually. That's just the 10 it looks like. So we have 10 times, and then let's bring in the absolute value terms. So that's x and y squared. And then square roots, we're square rooting three things still. The 3, the x, and the y. So times the square root of 3xy. All right. Last example I'm going to ask you all to do today is number 4. Again, treat it separately. Work on simplifying 3 times root 28. Separately from simplifying root x to the 5th. Separately from y to the 4th. Do your very best. This is the last one we got for today. Again, we'll save the backside of this for tomorrow. All right. I know everything kind of looks a little scrunched here. Maybe keep it in mind just as you're working on the practice problems here. Give yourself plenty of space to kind of create these factoring trees. You could even write them completely separate like what we did with the previous one, that we have plenty of work to kind of think about each term individually. So the 3 root 28, largest perfect square that divides 28, it's just 4. 4 is the only perfect square that divides 28. So I'm going to factor 28 to be root 4 times root 7. Square root of 4 is 2. So this is really 6 root 7. Ooh, I made a mistake here. This 2 should be a 6. All right, then x to the 5th. I'm going to factor that. So it's x to the 4th, or root x to the 4th times root x. Root x to the 4th is x squared. Since we're dealing with even roots, I should have absolute value brackets around it. Again, they're not necessary because x squared is already positive. Then root y to the 4th does not need to be factored. That is just going to be y squared. Since we're dealing with even roots, I am having absolute values on my radar. Once again, y squared is positive no matter what. So you actually do not need the absolute value brackets here. So answers that are simplified here are 6. Absolute value of x squared, y squared times the square root of 7x. Or The best answer is not having the absolute value brackets and saying 6 times x squared times y squared times root 7x. Again, absolute value brackets, I won't count them wrong. I want us to have them on our radar. But because of the squaring, they're not necessary. All right, that is it